Okay, thank you everybody. And today I'm really pleased to give my presentation on thinking up beyond the mean, associations between gestational exposure to chemicals, autistic behaviors using quantile regression. Before I begin, I just want to respectfully acknowledge that the work that I've done was done on the saber-tooth, Quequitlem, Squamish, and Musqueam nations. So just a quick overview of my presentation, and it will have three general parts. First, I'm going to give you a quick overview of what quantile regression is. Then I'm going to be talking about a research project that actually used quantile regression. And finally, I'll give you some practical advice on how to use this method in your own research. So first, I have a question for you guys. Have you heard of quantile regression? Are you familiar with it? And I'm looking at the responses, kind of, okay, never heard of it. Oh, some people have heard of it, but most have not. That's kind of what I expected. Okay, so this is kind of what I thought, that most people are not aware of it. That's totally okay. Actually, I'll share the. That's totally okay. I'm assuming you know nothing about this method. I'm going to teach you more today. My next question for you is, do you think that the effect of chemicals is generally going to be the same for all children? So almost everybody is saying no, and it kind of intuitively makes sense. Maybe some chemicals affect more people more than others. So what's get you thinking beyond the mean? So during the COVID-19 pandemic, as many of you are aware of, this had a lot of negative impacts, and one of them was students learning. So for example, in America, test scores dropped by 6 points on average. That's among all students. But something kind of interesting happens when you look at only the students with the lowest math test scores, people in the bottom 10th percentile. Their scores drop by a whole 12 points, which is twice as much as the average. Another example, where the interesting example, is with obesity. As you know, obesity is becoming more and more prevalent, and the average BMI is increasing over time. But this paper here makes a really interesting observation that not only is the BMI increasing a little bit over time, not just the mean is shifting over time, the entire distribution is becoming more skewed. And this is what I mean. So instead of the distribution moving uniformly over time, what's happening is people with higher BMIs are becoming more and more prevalent. Or in other words, the extreme right tail of the distribution is moving faster than the rest of the distribution, and so the distribution becomes more skewed over time. Now, all this suggests that if you're a quantitative researcher, maybe it's time to start thinking beyond the mean. And one tool you can use to do that is called quantile regression. So in contrast with linear regression, which is a more conventional method which finds the change in y for every 1 unit increase in x on average, with quantile regression, you can model the xy relationship at specific parts of the outcome variables, or y's distribution. And so let's visualize this a little bit. So I have some simulated data here. And first I use linear regression to create a regression line. And as you can guess, this line goes right through the middle of the data. Next, I use quantile regression to model the 10th percentile, or the lower tail. And this works by giving extra weight to the data points at and around the 10th percentile. And when this happens, we see that the xy relationship is relatively weak because the slope is rather flat. Next, I model the 90th percentile, or the upper tail of the outcome variables distribution. And I found that when I did this, the xy relationship was especially strong because, as you can see here, the regression line has a especially steep slope. So this indicates one of the possible benefits of quantile regression, that if you just model the mean, you might miss certain insights that you could find if you modeled the tails too. Quantile regression is really useful if you have a research question where a particular subgroup may be of interest. Like say you're looking at the effect of air pollution and birth weight. You may have an explicit interest in the low birth weight babies and want to know about the factors that affects them the most. And this is relevant for the paper I'm going to talk about today. Maybe you're looking at the relationship between chemicals and autism, and you may be most interested in the child who have the highest degree of autistic behaviors. Or maybe you're looking at, say, air pollution and asthma, and you want to see what the risk factors are specifically for the people who have the highest asthma scores. Some other benefits of quantile regression is that is more resistant to outliers and it may have fewer distributional assumptions. So with that said, we can move on to talking about this paper that was published in the American Journal of Epidemiology a couple years ago. So first, a little bit of background information. I'm sure most of the audience is aware of this, but we are exposed to many chemicals all the time. Over 140,000 chemical agents have been synthesized since the 1950s. Of these, 5,000 were produced in very large volumes. Another question I have for you is, do you think these mass manufactured chemicals are thoroughly tested for safety before they're released out to the masses? And I'm getting lots of no's, lots and lots of no's. Yeah, so basically, most of you said usually not. And that's right. So uh, many people who are experts in chemical regulation and safety policy have flagged this as an issue, that chemicals are being released without proper insights about their toxic properties. And it's only once researchers like us find that they're toxic, then they get taken off the market. But by then, a whole new chemical has taken its place. And another 10 years, we got to figure out if there's anything wrong with that and regulate it as well. It's basically a big game of whack-a-mole, also called regrettable substitution. Now, these chemicals can have impacts on a wide variety of our body systems. Their impact on the cardiovascular and respiratory system are responsible for a lot of mortality. They also can affect reproductive systems, immune systems, and the endocrine systems. But one thing I'm really interested in is their effects on brain development, because when a chemical affects brain development, that can have lifelong consequences, where this can impact your well-being, this can impact your ability to be economically successful, make money, in other words. And one of the many ways we can assess whether or not a chemical is assessed with neurodevelopment is to see if it's associated with autism. And this is because autism is thought to occur because of insults or perturbances that happen during brain development. So if something affects associated with autism, probably means it's impacting brain development. Now, autism, if you're not aware, it's a neurodevelopmental condition which is characterized by traits like having reduced communication abilities, having strong interest in specific areas, or exhibiting repetitive behaviors like arm flapping. And the modern understanding about autism is that among all humans, there is variation in cognition, variation in how we interact with the world and how we think. And people who are autistic are on the upper tail of that distribution, if you will. And I'm just going to say a few words about the neurotoxic chemicals I'm going to talk about in this study. So one that I'm sure you've all heard of is lead, and it and other metals have had a tremendous public health impact because of their neurotoxicity. Another group is called persistent organic pollutants, which, as the name implies, they're very persistent. Now, these chemicals, they tend to bioaccumulate up the food chain, which allows them to greatly impact ecosystems, aquatic systems, our food, dairy, so on. Examples of persistent organic pollutants, or just POPs, include organic chlorine pesticides and polychlorinated biphenyls, or PCBs. Another group of potential neurotoxic chemicals are plasticiders, which include phthalates and phenols. And now, phthalates and phenols are distinct from what's called microplastics. These chemicals are basically added to plastic to help give them certain characteristics like flexibility or being waterproof. Now on to the methods for this study. So in this study, we used data from the MIREC, or the Maternal Infant Research on Environmental Chemical Study. It is the largest environmental epi cohort study in all of Canada. It recruited about 2,000 participants during the first trimester of pregnancy across 10 major cities. A subset of them from 6 cities were followed up with when the child was 3 to 4 years old for us to do in-person neurodevelopmental visits. In the study presented today, we restricted to people who had complete data in all cases, which is 478 mother-child pairs. Next, we used a tool called the SRS, or the Social Responsiveness Scale, to assess the relationship between these chemicals and autistic behaviors. This is basically a questionnaire that parents fill out, and from here on in, I'll be referring to SRS scores and autistic behaviors pretty much interchangeably. A quick note on statistical analysis. I first created linear regression models. I log2 transformed all chemicals, and we used only first trimester chemical concentrations of chemicals, and we control for all the confounders you see here. So for my quantile regression analysis, I used actually a Bayesian approach. That I'm not going to talk too much about that Bayesian approach because it's actually not too relevant for this part, but I used it to model the 10th, 30th, 50th, 70th, and 90th percentiles of the distribution. And you may see in some of my figures that some of the confidence intervals are dotted. That means that some assumptions weren't met, and this meant that I had to widen the confidence intervals to address those unmet assumptions. So one thing I'm just going to quickly point out is that this Myrick sample is not representative of all Canadian pregnancies. Participants tend to be older, have better education and income, and have lower chemical concentrations. And now on to the actual results. So first off, we see the relationship between gestational light exposure and SRS scores. And using linear regression, each doubling in concentration was associated with a 0.5 increase in child SRS scores, which is a pretty mild, in this case, not significant relationship. But when we think beyond the mean, and I used quantile regression, we see that this relationship is especially strong at the 90th percentile of the distribution, or in other words, the relationship is stronger at the upper tail. And I noticed what I called a monotonic trend, where these associations got stronger when we went from the 10th to the 90th percentile of the distribution. So what does this mean? So not only did the linear regression model find a small positive association, which represents a relatively minor shift in the mean, we found that the distribution tends to stretch or get skewed in response to light exposure because the associations were especially strong at the upper tail. In other words, the distribution, the right tail of distribution moves at a faster rate. For the next, we saw similar kind of results for other metals too, including arsenic and cadmium. That being said, the results were less clear for mercury and manganese. Next, for the plasticizer chemicals, namely BPA and BPA, MBP, MCPP, and DEHPs, we saw the similar kind of trend. The relationship was stronger at the upper tail compared to the mean, and associations tended to get gradually stronger from the 10th to the 90th percentile. One thing where this trend was kind of reversed was MEP, which is a chemical often found in cosmetics, where it was associated with a decrease in SRS scores. And this relationship this inverse relationship got stronger as we modeled higher percentiles. The results were a little bit less clear for the persistent organic pollutants, but we did see for one pesticide, beta HCH, the relationship, we saw another monotonic trend. Associations are stronger at the upper tail than the mean. And in transnonachlor, we kind of saw a little bit of an opposite trend where associations got weaker as we went from the 10th to 9th percentile. And the results were a little bit less clear for the remaining chemicals. All right, so what does this all mean? Let's put it all together. So in this study, we found that chemicals like lead, cadmium, arsenic, BPA, some phthalates, and beta HCH were associated with increased autistic behaviors. And this result is generally consistent with the overall literature. And something that was really interesting was that in many cases, these results were especially strong among children who have a higher degree of autistic behaviors, which are the exact children that we may have a special interest in. We don't have an actual mechanism for why this is, but it may be that these children possess latent characteristics, or in other words, they have certain properties that may make them more susceptible to the neurotoxic effects of chemicals, which suggests that more effect modification analyses are needed. Another interesting finding is that MEP and transnonachlor were inversely associated with autistic behaviors. This may be due to unmeasured confounding, due to bias that was not addressed, or due to chance, as again, these results were actually not super strong. It could have just been a chance occurrence. But either way, this still suggests that these chemicals are associated with brain development, even if it's kind of not in the direction we are anticipating. And finally, these results suggest that quantile regression can unveil extra nuances, extra details that would be missed had you only used a more conventional method like linear regression. It also suggests that the chemicals not only cause the distribution, or not only are associated with the distribution shifting uniformly, but also stretching. And overall, this suggests that quantile regression deserves more attention in environmental epidemiology. A few papers have used it, but it's not really a very well understood method. Okay, with all that said, let's give you a little bit of practical advice on how to use quantile regression. So first off, quantile regression, the frequentist approach is fairly easy to implement. You just need to load in the appropriate package. You create your regression model similar to how you would make any other regression model in R. And the only thing that's really unique is having to manually specify the tau, which represents the quantile of the distribution you'd like to model. Now, one thing to note is that unless you have a very high sample size, I would avoid modeling really high or really extreme taus, and for example, the 99th or the 95th percentile, because the confidence intervals get very wide very fast as you start going to the extremes. Another thing, another possible limitation from a more practical perspective is that if your analysis is already really complicated, you have lots of exposures, lots of outcomes, having a lot of taus can just kind of result in a lot of results. So you might want to consider not having too many taus, maybe having the 10th, 50th, and 9th percentile. But that being said, if you have a more straightforward analysis, including more and more quantiles is useful because then you get a better picture of what's happening throughout the whole distribution. The one part about quantile regression that is more complicated is the confidence intervals. And most people don't need to worry about this too much, but I will just quickly note that when your sample size is under 1,000, the quantreg package works by using the rank-based method for calculating confidence intervals. This is an extremely esoteric method for calculating confidence intervals. I don't think any other method uses it, and it has some kind of unusual properties. Like it can result in confidence intervals that are very asymmetric, and sometimes in rare circumstances they can even extend into infinity. So if you're a bit afraid of that, then I would consider using the bootstrap approach instead. And another potential thing to keep in mind is that when your sample size is over 1,000, the quantreg package will calculate more traditional walled-based, also known as direct inference confidence intervals. This is the strategy that most linear regression methods do. It does this because it's a more computationally efficient way to do it, but on modern computers, it really isn't even that big of a difference. The problem with these walled-based intervals is that they tend to be too narrow. They don't have the appropriate width. Like the 95% interval doesn't cover the appropriate value 95% of the time under certain circumstances. Whereas this is less of an issue for the rank and bootstrap method. So you may be wondering, when is quantile regression useful? When should I consider using it? Well, if your errors are heteroscedastic, then it may be useful. As we kind of saw in this earlier example, you can see that the residuals are not constant. They're kind of fanning outwards like this. And under this condition, when you use quantile regression to model the tails, it may have different effect estimates at the tails versus the mean. So for this reason, I see quantile regression as a potentially useful method for complementing an existing analysis. It could be put in the supplementary material just to kind of to divulge a little bit more insights. And again, it's especially important if your outcome variable maybe like you're really interested on the tails than you are than the mean. When else is quantile regression useful? Well, I would say it's pretty useful. You should consider using it if your outcome variable is continuous. This could include like something like income, for example, like the amount of money someone earns, or BMIs, or some sort of anthropometric measurement, like just a waist circumference, something like that. One thing I'm going to talk about in the next couple of slides is a special case. If your outcome variable is discrete or a count variable, that means it only takes on values of like 1, 2, 3, but not like any decimal places. There are some considerations I'm going to talk about in a minute. However, if your outcome variable is binary or categorical, in my opinion, I don't think quantile regression is particularly useful. That's because the whole point of quantile regression is being able to kind of model the whole distribution, and a binary variable doesn't really have much of a distribution. That being said, there's some people who've created some really, really fancy models where they are able to conduct quantile regression on binary or categorical variables. I don't think they're very common. It's kind of used more for machine learning or econometric uses. But I'd say if you're a health researcher, you kind of want to look across the whole distribution. It's not really that useful for binary outcome variables, but maybe I'm wrong. Maybe someone could correct me in the future. And with that said, I'm going to present you a very small snippet of this paper that was, I thought it'd be published by now, but it should be published sometime next week, hopefully. So as I was saying with discrete outcomes, they're kind of an issue with quantile regression because the frequentist approach to quantile regression assumes that the outcome variable has a nice, smooth, and continuous distribution, whereas a discrete variable like 1, 2, 3, 4, it's going to be all spiky like that. And this is kind of an issue because in medical research, we often use discrete outcomes. Like again, if you have some sort of measurement that's it's only accurate to the nearest whole number, that's going to be a discrete variable. With SRS scores, that's only measured to the nearest whole number. It's like 40, 41, 42. That's why I had to use the Bayesian method. That's what to address this issue. Similarly, IQ scores take on values of exactly 100, 101, but you get my point. Discrete outcomes are kind of common in medical research. And this can result in some really implausible, unusual results. As you can see here, I ran a regression model, and I see that my effect estimate is equal to exactly 0.000. And my other effect estimates are negative 2.333, 1.333, 1.6667. This is kind of strange. But the thing is, nobody did anything wrong. This wasn't due to a software mistake. This wasn't because of a software glitch or anyone making a mistake in the package. This is just kind of how quantile regression works. And when you think of like medians, it kind of actually makes sense. Like say you're taking the median of a set of whole numbers. Like say the median of 1, 2, 3, 4, 5. The median of that will be 3, like exactly 3. And that's a bit of an oversimplification, but that's kind of how it works, where you can get these whole numbers or fractions based off of the algorithm. So to explore this further, I simulated 1,000 data sets and used quantile regression to analyze them. And in these relatively simple data sets, I saw that every single time, all of the effect estimates were equal to whole numbers, or the effect estimate is equal to exactly -2, or -1, or 0, or 1, or 2, or 3. This is kind of unusual. Like you can imagine if you have a high enough sample size, you should be able to estimate your effects to a couple decimal places. But getting whole number values is a little strange. So what do you do in this situation? Well, there's two possible workarounds to this issue, even though it's not really an issue, it's just kind of a quirk of how the method works. One of them is called dithering, which also known as jittering, and it works by adding random noise to the outcome variable, so that way your discrete outcome has an artificially smooth distribution. And when I applied dithering, everything else was the same. The only thing that's different is I'm applying dithering. Now that the distribution of effect estimates has a nice normal distribution, which is what we were expecting. Whereas without dithering, we were just getting these kind of strange whole number values. Another possible alternative is to use a Bayesian approach, which has mathematical properties that can avoid this issue entirely. And using the Bayesian approach in the same data, we kind of get a similar idea. The distribution is a nice normal distribution, which is what we were expecting. So in this paper, I asked the question, what should you do? Should you just leave it alone and these rounded results are not that big of a deal? Should you apply the dithering method, which is really easy to implement? Or should you apply the Bayesian method? So I generated a bunch of data sets, and what I did was I tested their performance by looking at the variability of the point estimates. And I found that dithering, even though it's a really easy thing to do, improved the variance by about 5 to 40%. Now, this improvement was especially apparent when the sample size that you're modeling is high, or when the exposure variable you're modeling is either discrete or a binary variable. When the exposure variable is continuous, like say continuous lead concentrations, the benefits were not as noticeable, but there still was something. Next, the Bayesian method actually had even better variability, specifically when sample size was lower. It had a even greater improvements. But that being said, when the sample size was a bit higher, the Bayesian method and the dithering were about tied. All right, so let's just quickly summarize this. So as I said before, when you're doing quantile regression and your outcome variable is discrete, i.e. it lacks that nice smooth distribution it assumes you have, then you may get a pattern of results that you might not expect. Two possible workarounds for this are dithering or using a Bayesian approach. Now, dithering is very, very easy to implement. You just need to add random noise to y. That's it, you're done. You may need to set a c to kind of keep your results constant, but other than that, it's pretty easy to do. And it resulted in a clear improvement in performance. The other method is using the Bayesian method. It is much more computationally demanding. It's more complicated. And it also had some other issues that I don't have time to address in this presentation, but when that manuscript gets presented, I'll kind of talk about, possible limitations associated with the Bayesian method. All right, so before I finish up, I just want to quickly acknowledge the MyArc participants who went through, donated a considerable amount of their time, filled in a lot of paperwork, got many needles jabbed into their arm to make this research possible. I'd also like to thank always nice people who help contribute to this research, and to you for listening. Thank you.
Thank you very much, Josh. I really appreciate that